Good morning once again. Right now I'm going to dive into integral calculus. Yeah, I was supposed to cover it last weekend, but yeah, I hadn't fully prepared, so maybe I can start right now. So integral calculus or integration is one of the two operations in calculus that we cover. The other one is differentiation. So differentiation focuses on finding the rate of change of a function, while integration is essentially about finding the total accumulated quantity such as area under curve, or let me just say it's in simple terms integration. In simple terms, integration is like the reverse of differentiation. Then we have types of integrals. We have the indefinite integral, which we can term as the antiderivative. Yeah, so it represents the general form of the function, but without bounds, like there is no interval. So after evaluating it or after finding the integral, we normally add a c for a constant, since the derivatives of constants are zero. Then here we have a table showing the common integrals or the basic rules, though there are more than these, but this is just a sample. We have the k constant. For k is a real number, then the reverse, or let me say the integral is kx plus c. You see that we've added here, it was, let me say it's x to power 0, then here when we reverse it or when we integrate, it's an x to power 1. Yeah, then for an x to power n, yeah, okay, we're going to look at the different types of integration or the techniques where we shall see where how to come up with some of these expressions. The other type is the definite integral. It represents the area under a curve, but here it's bounded. It has bound, let me say from x being a, and for x equal to a and x equal to b. Then the techniques of integration. Yeah, integration relies on various techniques depending on the form of the integrand. Integration by substitution is one of the techniques, and it's what we're going to look at first. Okay, so integration by substitution is used when the integral contains a function and its derivative. Yeah, or when we have like an expression whereby expanding it, for example, this one in this example, we figure that if we are to expand to the power 10, it would be lengthy in working out the integral. So we just substitute the inner expression x plus 3, substitute by with, let me say, u. Yeah, then we rewrite the integrand, but in terms of u. Yeah, then these are the steps that we take. Yeah, so yeah, I think we are familiar with some of these steps. So we see that this expression, when you substitute for x plus 3 into u, this is the expression that we get. Remember, even the bounds in this expression, they're in terms of x. So we also have to switch them in terms of u in order to get the final answer. However, when we're dealing with u substitution in indefinite integrals, those that don't have bound, you have to get the final expression in terms of x, you have to switch it back to x. Yeah. Then that's another example, but here it's more like a composite function. Okay, a compound function or a product of two functions. Seeing a trigonometrical function and an algebraic function. So we substitute for the angle, then we follow the very same steps, yeah, to get the final expression. Then the other technique is integration by parts. Yeah, so it is used to find the integral of a product of two functions. It is derived from the product rule in differentiation. If you're to integrate the expression of product rule in differentiation, we get this expression of integration by parts. Yeah, and yeah, this is the formula. Yeah. So this u, or we can call it fx, is a function of x, or whatever variable we use in the expression that you're trying to integrate. Then the dv, or g prime of x, is the derivative of the other function or the other part of the integrand. Then the du is the derivative of the u, and then the v is the integral of dv. So the steps of choosing which one to take as the u and the dv is, one of the commonest rules is the Leiter rule. Yeah, so the Leiter rule is used to choose which function should be used as the u. So whichever comes in this order, whichever function comes first in this order is what we take as the what? As the u. For example, in this function x is equal to, sorry, x into cos x. Using the Leiter rule, the algebraic function x that we see comes before the t. The t is the trigonometric function, so we take the x to be the u, and then the cos x to be the dv. Then we follow the procedures. This is another example, or the first example under integration by parts. We are seeing a function, okay, or the integrand as 2x times sine x. This is an algebraic function, and then this is a trigonometric function. So according to the Leiter rule, the a comes before the t. So we take the a, which is the algebraic function, to be the u, and then this is taken as the dv, which is the same thing in this expression, in this statement, sorry. Yeah, so from integration by parts, yeah, using the other expression above, these are the steps that we follow, yeah, to get the final answer. Then the next technique is use of partial fractions. Partial fractions, we apply it when integrating rational functions. Yeah, all functions where the numerator degree is greater than the denominator degree. Yeah, for example, we say like x over x squared plus 1. There the denominator degree is greater than the numerator degree, so we can apply use of partial fractions. So yeah, this is another example. We see that the greatest degree of x here is 2, and above it's 0. Yeah, because any number to power 0 is 1, so the x term here is 0. So what we do, we divide the fraction. Okay, we factorize the denominator here, and then we divide, or we separate, I don't know which term to use, or split the function of the denominator into, okay, something similar to this expression, where a and b are constants, to find the, okay, how to represent the numerator. So after simplifying this, or after solving it, we come up with an expression similar to this. Yeah. All right. Okay, after doing this, we have to generate two, how can I say it? We have to come up with two equations so that we can get the values of a and b, and then we fit them back into this equation. Realize that it will be much simpler to solve this directly by using partial fractions rather than solving this directly using any other method. Yeah, that's another technique. And then we have trigonometric integrals. These are integrals involving powers of sin x or cos x, tan x, etc., or trigonometric functions. For odd powers of sin x, cos x, we use that triangular, is it equation? I think that's what we used to call it, to write the expression. Then for odd powers, we use the double angle identities. Then we have an example here. 3 is an odd power, so we use the triangular expression to represent it. Okay, just rewrite it in that using the triangular expression, and then for even powers, sorry, we use the double angle identities. Yeah, I'm quite sure the level that you are on, we've used them before. Maybe right now it's more like a recap. Then another technique or rule that we use is trigonometric substitution. It's used for integrals containing expressions that are similar to these three. Yeah, there's a way we use to derive them, but yeah, it could take some good time, but it's not difficult. However, these are the identities that we use, all the substitutions that we use. Normally, these expressions are taken in, I think, denominators. That's why we normally substitute them, though there are some cases whereby we have to substitute them in what? In single expressions, all those that are not rational. Then, yeah, there is the tan substitution, then the sine substitution, and the sec substitution. Yeah, I think that's all that I have for now. I think the following meeting I'll be handling sequences and series to be more